All right, good evening, everybody. My name is Mike Moyer. I'm the section chair of SAE Southern California. We're happy to have you tonight for a really interesting presentation, along with our SAE MidCal section. So I'd like to recognize Joey Penniman as well, who's the section chair of that. I guess together, since we're doing a lot of things virtually these days, we're not geographically constrained. So whether you live in Silicon Valley or you live in LA, you don't need to fight traffic anymore. So welcome. Just a quick note about the SAE sections. Of course, we are all volunteer organizations, and we're here to bring interesting technical content to you, our members. So appreciate you that you're here. You can find us on saesocal.org. We also have a YouTube channel. We're actually streaming live right now. We are sending out old school mail flyers to all of our membership to also talk about all of the events that we have coming up in calendar year 2021. So we hope you have a chance to check it out and come join us for all the interesting topics that we have, despite all of the constraints that we all are under personally and professionally these days. Without further ado, I would like to introduce Bill Visnick, who is going to talk about our topic tonight and then make further introductions. So Bill, over to you.
Well, maybe while we wait for Bill, I can chime in here. My name is Joey Penniman. I'm the section chair of the MidCal section of SAE. Like Michael said, we're probably going to be doing more of these types of events virtually in the future. I've been focusing primarily on student outreach in the MidCal section, but moving forward, we're probably going to be hosting more events similar to this, tech talks and things of that nature. The SoCal section has been really helpful to facilitate the sort of the collaboration for events like this. So you'll likely see more of these events in the future, and hope to see you guys at future events as well. Bill, maybe, there we go.
Okay. I'm hoping everyone can hear me now. Sorry, that wasn't me. I think we'd gotten crossed up there on getting the video started. Anyway, thanks everyone for joining us. I assume everybody can hear and see me now. I'm the editorial director for SAE's Mobility Media. I'm anxious to hear about this tractor too. It's the first time I'm hearing this presentation as well, so I want to hear all about it too. And let me introduce the two people who will be speaking tonight and doing the walk around and the presentation. First is Zachary Amahundro. I hope I did that right, Zach. Co-founder and chief technical officer for Monarch. Over the past 2 decades, Zachary has developed hundreds of tightly integrated, intelligent electromechanical systems, bringing a full system design perspective to the development of never-before-seen products. Prior focused areas include mining robotics, energy storage systems, electric vehicles, by-wire autonomous cars, and automated agricultural equipment like we're going to see tonight. Just to show off, he holds a double degree in electrical and mechanical engineering and a PhD in robotics from the Robotics Institute at Carnegie Mellon, which is just east of me here. Along with Zachary, Chris Whitney, who is Monarch's head of automation, will also be doing a presentation or joining the presentation. Chris has been on the cutting edge of automation in Silicon Valley, Singapore, and his native England for more than 30 years. He has played key technical roles leading innovation at British Telecom, Hewlett-Packard, and other leading companies. He earned his bachelor's degree in computer science from Tassad University and a master's in information systems engineering from the London South Bank University. So with that, we will let Zachary and Chris take over, I believe. Can you hear it?
Hey, Monarch Tractor team, you might have to pause the video and reshare your screen with the check the share computer sound option because there's no sound coming through.
The Monarch Tractor is the world's best tractor. And it's the best tractor because it's electric, because it has automation capabilities, because of the incredible amount of data it can pull, and because it fundamentally changes farmers' economics, allowing them to be more profitable.
Monarch Tractor is that bridge that we can now cross and leave behind the conventional world and move forward in the beyond organic world.
Our tractor does everything your existing tractor does, and it allows you to start saving dollars and cents every hour you use a tractor. We're going to elevate your job from a tractor driver to a fleet manager. Your existing implement that you've been using for 20 plus years now is smarter and more sustainable just by attaching it to our tractor.
It's the combination of a conventional tractor, the utility of an ATV to pull tools and other needed supplies out into the field. It has the utility of a genset.
Pure electrification will reduce tractors' cost by $45 a day. From a profitability standpoint, it's a slam dunk.
This is something that is bigger than just your farm too. This is about sustainability at a planet level.
This isn't feel-good sustainability for sustainability's sake. These are using sustainable technologies to make farmers more profitable. So if you want to fundamentally improve your economics, go electric.
The future of farming will be bright. The future of farming will be beyond organic, and it's an exciting time to get into agriculture. And we're really happy and we're really proud of what we've been able to produce here at Monarch Tractor, and we cannot wait to share this product with you.
So yeah, that was obviously our marketing video, but I think gives you a pretty good top level view of what we're trying to achieve with the Monarch Tractor. So particularly for this audience, I think some of the key items are the electric aspect and the driver optional aspect, and how those two then enable the data and connectivity functionality of the system. So what we wanted to do is basically kind of give you a walk around the tractor and let you see some of the functionality and features that are in the tractor, and kind of get a little bit deeper into some of the technical details of what we're trying to achieve. So I think we have the video coming from Chris's phone, and so that's basically one of our tractors. And as you can see, being an electric tractor, that allows us to fundamentally reshape what a compact tractor looks like. So without the engine, we are able to create a front compartment that provides additional utility. So basically has the front bay to give you the utility of what you'd see on an ATV, for example. Often farms will have an ATV or UTV with just a small compartment in the back for hauling tools and goods. So we have that up front, and that is actually above our battery pack. So the battery pack sits below that to keep the center of gravity of the tractor down into the front, which for a tractor application is generally what you want if you're using heavy implements. And I think at a high level, right, what we've done is we've created a next generation tractor by borrowing technology from a few different fields. So much of the drivetrain is heavily leveraging all of the investment that has gone in on the automotive side. So a lot of the drivetrain components and the battery elements and the battery management system and all of those elements are leveraged from the automotive sector. A lot of the core tractor functions, you know, the axles and wheels and tires, obviously, and many of the hydraulic components, that is taken from the existing agricultural marketplace and kind of all of the components there. And then a lot of the control functionality and the kind of base layer intelligence, if you will, that's taken from a lot of the kind of autonomous vehicle development work. So a lot of by-wire systems, and then building up into the compute, which Chris will cover, which is largely in the roof. Real quick on, as we're kind of looking at the rear of the tractor, I'm not sure how familiar everyone is with tractors, but most tractors, they will have a power takeoff shaft or PTO, which you can kind of see hidden back in there. So this is a 540 RPM PTO, which is standard for the compact utility class. They will also have a 3-point link. Right now we don't have an implement attached, but you have 2 lower links and 1 top link. And so those links would be connected to any kind of implement. Additionally, you have the hydraulic connections. So you can see a few of the quick disconnects up top. So those are quick disconnects for hydraulic functions that would go out to an implement. A tractor is very much a universal work tool in the farm. And what makes it useful is the implement that you connect to it. You rarely see a tractor just being driven without something behind it or something attached to it. So really it's not just the tractor, it's the tractor plus the implement, which allows you to do useful work. And we have made the conscious decision to be fully backwards compatible with existing implements and existing systems, because many farmers will have, you know, barns full of different implements, and we want to be able to support all of that. And that also, you know, this is a new technology and a new platform, but we don't want to force farmers to completely redo how they do their operations or how they work in their fields. We want to give them a new, better tool rather than forcing them to redo core operations. So that's some of the bigger features that you can see. I think kind of the under the hood, we don't really have a hood obviously, but kind of under the hood, it's a fully by-wire controlled system. So steer by wire, drive by wire, brake by wire, full by-wire control, which enables the driverless functionality and the automation system. And it also actually allows us to simplify the control interfaces. If you look at a competing compact tractor, it'll usually have upwards of a dozen different levers and dials and different things that you can adjust, because it's a very mechanically driven, like, you know, mechanical hydraulic system. whereas the Monarch Tractor, everything is electronically controlled, which also means that we can have a layer of control loops that run on top of all of the systems. So we can actually get functionality out of the system that you might not expect from a tractor. Things like traction control or stability control, which you might be, are common in cars now, that becomes possible with a tractor when you have complete electronic control. And then that also means that there's a clean interface and a clean connection between the tractor-based platform and the autonomy and compute system, which allows us to do driver optional or driverless operation. And so to talk a little bit more about that and kind of some of the sensors and the kind of compute approach and autonomy approach that we have, I'll hand it over to Chris at this point. Chris, if you want to start talking through that aspect of the system.
Yeah, great. Thanks, Zachary. Zachary mentioned, he talked about pretty much most of our tech, which is down here. It's basically from the battery, the wheels, the axles, the steering, the powertrain, et cetera, et cetera. So that's kind of like the lowest layer of our technology, all the way through to the implement control, which is essentially these hitches, the PTO, and the hydraulics. Zachary also touched on the fact that everything that can be moved on this tractor, everything that we can control, like the wheels, the steering, the hitch, it's all drive-by-wire. So behind the seat here is the drive-by-wire capability. So kind of like the middle layer of our tractor here, the cockpit, is where most of our drive-by-wire is. And as an example here, this is one of the accelerator pedals, and you can see it's electronic. It's not a linkage thing. It's basically a servo motor which is attached to our drive-by-wire system. What that really means, as Zachary touched upon, is we can reconfigure this cab. All of the steering, the joysticks, the buttons, everything is electric drive-by-wire. So we can swap these things out. But it also gives us the ability to hook into this system computation-wise. Charging port here, standard electric charging. Another useful feature is the external power. So again, one of the reasons why we have this frunk here, for example, if you want to carry a genset or a welder, you can put the welder in here. You can plug it in. So as well as basically being a power workhorse in terms of torque and moving implements, the battery pack can also power external tools. Like, for example, if you're in the middle of a field and you want to weld some metal, you can carry a welder in the frunk, and then you can plug it in and weld. So it adds to the overall utility of the electric tractor, not just electric in terms of drive, but also being able to use electric tool sets. And even if you need to, and it becomes more of an issue with some of the farmers in, for example, Silicon Valley at the moment, to be able to power aspects of your house using the exportable power. So the middle layer is really all about control. Where some of the automation and the data tech comes in, as Zachary mentioned, is up in the roof. So we have a roof here. The roof for us provides a dual function. One of them is to protect a driver when the driver's in the seat. So falling object protection, rollover protection, standard for tractors. But it also houses all of the tech, all of the sensors for our autonomy. So the best way to think about this section here on the top, the kind of like the top of the sandwich, it's a very big computer with everything in there. And there's an umbilical cord which connects the roof to the drive-by-wire system, and from the drive-by-wire system to the rest of the tractor. So there's a lot of tech in the roof. Our GPUs and CPUs, which basically process all of the data and allow us to implement our self-driving routines, are housed in the roof. We have our sensor suite, which I'll go into in a little bit, but also the connection to the outside world. So if you see on the top, there's a couple of antennas there. This is a fully connected tractor. We have various ways of connecting this tractor to the outside world and to the cloud, where we have some of our Monarch applications. We have radio connectivity. Radio connectivity is important for two reasons. One of them is so that we can connect to a base station, which we use for low latency, low bandwidth communications across areas where you don't have very good cellular coverage or Wi-Fi coverage in the farm. And it also allows us to get our GPS corrections, which I'll talk about a little bit later. We also have a Wi-Fi access point. So if you want to deploy a Wi-Fi mesh in your farm environment so that you can communicate with the fleet of tractors across an IP network, you can do that. We have cellular connectivity, so that if you're within cellular range, you're always in command and control and data transfer with this tractor. And then we have a local LAN. So, for example, if you've got a mobile phone with our Monarch application on it, you can actually use the mobile phone to communicate externally with the tractor. I'll talk about some of those functions later on. So this is what most of the tech in the roof does from the network layer down. Our storage disks are in there. We have enough capacity in there to store all of the data that we bring up for probably about 2 days. We offload the data into the cloud when the tractor comes back to the base station for charging during the charging cycle, and then connected to the compute fabric we have up there. We talked about the connection to the drive-by-wire system, but we also have connections to our sensor suites. Two main sensor stacks that we have. One of them is a sensor stack that gives us very good positioning of the tractor and basically allows us to establish in autonomy terms the pose of the tractor. So it's very difficult to see again unless Kelsey puts the phone up there, but there's a dual GPS antenna configuration up there. We use 2 dual onboard GPS antennas so that we can get very, very, very precise heading. So we can orientate this tractor to about a degree of accuracy using that dual GPS configuration. We prefer to use that over more magnetic sensors because we can do a dual function with the GPS. We can get heading as well as get in positioning. Those GPS antennas also connect to a base GPS antenna, which sits at our base station. And then doing triangulation and using the radio connection. Typically, if we get good GPS coverage, which in most large-scale farming scenarios that we've been running this tractor in, we're getting, we can position this tractor to about a 2 centimeter of ground truth, which basically means if we really, really need to, we can geographically locate these tractors very, very accurately in the farm. We also have several IMUs on the tractor. IMUs in the roof, which enable us to basically calculate the pitch and roll, but also allows us to do some offsets because of vibrations and judder that you may establish when you're going across the field. So we can counter those when it comes into our visioning system. So with the IMUs and with the GPS and with the GPS RTK to the base station, also with wheel odometry and some visual odometry that we do. We have some very, very sophisticated localization algorithms. So if we're in a good GPS coverage, we have a very high level of truth. But if we fall down from GPS, we can bring in other forms of localization so that we can always maintain within a very high degree of confidence where this tractor is. As you can see, I keep touching this tractor. This is a working tractor. We just brought it in the field from the field today. It's been out doing its test runs at a vineyard that we have close to our Livermore office. Second sensor stack that we have is our visual stack. A lot of our autonomy is vision based. So I'll just take you around some of those. At the front here, we have stereo depth cameras, and we also have stereo depth cameras at the back. What this allows us to do is to basically get our object positioning at the front of the tractor and the rear of the tractor. What we're trying to do at any particular point in time is maintain a 360-degree, we call it a proximity map. It's basically, it's a viewpoint of anything that's around the tractor, and we classify those things. So if you notice here at the moment, these panels, they keep blinking from, I'll walk away from them. If we keep walking, just walk away a little bit. It keeps recognizing us. And we use our corner panels in the roof as kind of like a signaling mechanism to people that are around the tractor. And so at the moment it's showing the Monarch butterflies, but if I walk in, that's going to flick to a human presence, a human detected. So we use it as a HMI capability. But to do that, we're using the proximity map to tell us at any particular point in time what's around the tractor. So it knows that I'm here. It knows that I'm here. It's watching me. Everything's being recorded. So all of my interactions around the tractor are being recorded. The events around the fact that I'm here are being sent up to the cloud. So if I'm a farmer on my mobile phone, I can start to get events which says, oh, Chris is near the tractor, what's he doing there? Or maybe at night, if the tractor's in the barn, sitting by itself and everyone's asleep, it acts as a sentry watchdog type capability. So the front and the rear stereo cameras, that really gives us the depth perception. And then we have monocular cameras all the way around, which basically give us the 360-degree view of what's happening around the tractor. So with the exception of a couple of very narrow blind spots, we get a complete panorama of what's happening. We use all of that information with the CPUs and the GPUs in the roof to calculate that proximity map. And so we use neural networks, so everything is classified. So all of the objects that are around that we've trained our neural networks on will be recognized and classified, and we will position them around the tractor. And that forms a basis for safety as we're moving the tractor around the farm. Sets of guardrails. So for example, if the tractor's moving forward and I'm standing in the way, the tractor will stop. We have a safety guardrail. If I put my hand too close to this spinning PTO, the PTO will stop. So safety is kind of like the #1 factor when it comes to automation. This is a very big, heavy torque machine running around the farm in various autonomy modes, sometimes with the driver sitting in the seat, sometimes with the driver away from the tractor, sometimes the driver will be away in the barn. So safety is paramount. So a lot of our algorithms in the roof are really to look at the safety aspects. Is the tractor going too fast for the conditions? Is there people around the tractor? Are there holes in the way which are going to deviate the course of the tractor? Are there big rocks in the way, which means we'll need to lift the implements? Those are all of the control decisions that are being made in the roof to make this a safe tractor using the sensor suite that we have around the tractor. There's another sensor that we have on the roof. It's to the back here. It's the weather station. We're very interested in weather when we're looking at autonomy of farms, because weather plays a very important decision to determine what operation you should be doing. So for example, if you're spraying herbicides in a farm, you've got to be spraying when the wind speed is below a certain speed. Otherwise, the spray just goes on and can, there's certain liabilities in the farm for that. So we tie in the information from the weather sensor as well as another data set for our control decisions. So the roof on the Monarch Tractor it's fairly complex, fairly sophisticated in terms of its capabilities with respect to planning, perception, decision making, and also its connection to the cloud, where we have our Monarch cloud, where a lot of our applications around mapping, mission planning for planning the operations on the farm will take place. So it's electric at the bottom, drive-by-wire in the middle, self-driving, data-rich at the top, and in the cloud is where we have a lot of our data analytics. So I'd say, just in terms of a whistle-stop technology overview of the tractor. One more thing here, we have a touch screen, so if people are on the tractor, they can actually interact with the roof. And we show various things on the touch screen. For example, we can look at various metrics around what's happening at the moment, the wind speed, the wind directions. We can get camera views based on what we're seeing. So if you want to be driving the tractor just looking forward, and you don't want to be turning your head all the time to see what's happening behind you, we can give you viewpoints of what's happening behind you. Yeah, I hope that gives you a good overview of the tech that's involved in providing this electric automated tractor.
Zach, oh, you're good.
Yeah, I think that was the quick overview we wanted to provide. I think we were thinking that we could kind of maybe open it up to questions at this point, and make this a little bit more interactive based on what people are interested about or curious about with the Monarch Tractor.
Okay, great, Chris. Thank you, Zachary and Chris. Great walk around there, and we've got a lot of questions. I have a few questions. Being that I'm the moderator, I guess I'm going to jump in and do one first, because That's what I do as the moderator. And this really does kind of piggyback on one that came in earlier. I was curious when I first saw some of the early information about the tractor, about battery capacity and battery sizing. Are you intending to make sort of just a one-size-fits-all battery, or will the customer be able to kind of choose battery capacities? How are you planning to work that?
Yeah, so on the battery capacity side, we have a very large battery. It's actually bigger than kind of any of the existing electric vehicles out there. From a capacity standpoint, we're well above the kind of what you could get even in a top-end Tesla or equivalent. And that's because the farm work use case is quite challenging from an energy standpoint. So we've, kind of gone very big on the battery so that the farmers have maximum operating time, and so that they can generally get through a shift of operation, depending a little bit on what the specific application is. So in that sense, that is the battery size. And I think the other aspect of that is that we also have designed the Monarch tractors to support a battery swap. So for those cases, it is a farming. Farming is very much a business and an operation for most people. And so in those cases where it's harvest and I need to work continuously, we've designed the system to be able to support that. So if you need to do continuous operations, you can do that via a battery swap. But the battery sizing is basically set to targeted at allowing you to do a normal shift without having to do any battery swap. But for those, peak harvest times, we have a mechanism to support that as well.
Zach, are you just reluctant to name the battery size, detail in particular? Is that still proprietary, or what?
It is a little bit, and honestly, battery technology is continuing to progress. So even in the last 6 months, as we've been continuing to develop the battery and the battery suppliers, the numbers have been creeping upwards as the battery technology, driven by the automotive industry primarily, keeps getting incrementally better.
Sure. Are you using an automotive industry supplier? Is it one that everybody would know?
Probably.
Okay. Okay.
Yes.
Oh, you're just not going to say anything here, are you?
Not on that front. We have talked to, I forget what we're at now, I think 9 or 10 different tier 1 automotive suppliers, and are in serious conversations with 4 of them. But I would prefer not to disclose the specific 4.
Fair enough. I'll quit acting like a reporter here and more like a moderator now.
No, that's fine.
And look, several of the questions that are coming in, Zach and Chris, are asking about the sensors and, obviously the conditions and the weather situation and that you would have in a farm type situation, or, just outdoors in general. And how robust are they in terms of inclement weather? Do you have sensor capability to overlap? For example, is there LiDAR to back up radar? That kind of stuff. Let us know a little more there.
Yeah, I can take that, and you can comment if you want, Zachary, as well. We've been doing a lot of field testing. You can see this tractor's been out in the field for a long time under various weather conditions, rain, fog that we have up here, as well as a lot of dirt. So there's 2 ways we answer that question. One of them is we have a sensor suite on at the moment, which we feel pretty comfortable with, both in terms of the capabilities we get, but also the conditions on the farm. I've had a lot of experience with LiDAR. I've used LiDARs in different forms. Obviously, for a tractor like this, you want to be using solid state LiDARs rather than rotational LiDARs, just because of the G-forces and the vibrations that are involved. Solid state LiDARs come with a particular price tag at the moment, which are slowly coming down. But also LiDARs, as you know, the fidelity of the information you get is very, very subject to the conditions that you have. And so one of the things that we learned very quickly when we were running these tractors with implements such as sprayers, a lot of the time your tractor is surrounded, particularly at the back, in a very fine mist. And so, we looked at LiDARs in terms of the technology, and we've been comparing the point clouds that we can generate from LiDARs with the optical point clouds that we're starting to generate from the cameras. With the combinations of the cameras that we have here, some of the depth cameras, the clarity of the quality of the lenses we use in our molecular cameras, we're not noticing any real problems in terms of the operational range of how you would use this tractor. One thing we do, and again, it's part of our safety protocols with respect to automation. The same way with our localization, it's the same thing with our clarity index, with our cameras. We have clarity or confidence indices which go up and down depending on what you can sense at any particular point in time. It doesn't really matter whether it's because it's misty, or as you can see with some of the cameras that we have at the bottom, whether they get muddy. Our autonomy algorithms will always adjust based on what we can see. Basically, it's a safety first situation in the farm. If you can't see, if you're blinded, if you've got some sunlight coming in and you can't make a decision, then slow down and stop. So I would say at the moment we're predominantly vision in terms of the object recognition. We keep our eye out on LiDAR and on radar technologies. But at the moment, the technology choices we made for the sensors in the roof is predominantly vision.
Okay, so in other words, right now the sensor suite, Chris, is only vision and not spec'd right now for LiDAR or for radar.
Well, I would say for us, in terms of the compute and the algorithms, we're sensor agnostic. I mean, basically, the way that we build our algorithms in the middle is to build a proximity map. And so what we're looking for in the proximity map, it's very similar to a point cloud. We're looking for evidence that at a certain position in the cloud, a certain position in the point cloud, we can classify that to a particular object. And so when the information actually gets down to our proximity map, we don't really know whether it's come from a camera, from a radar, from a LiDAR. The outer layers of our algorithms deal with that. So the moment the most information that's coming in is coming from our depth cameras and from our monocular cameras. We can quite easily plug a LiDAR. We could actually, if you want, it's quite easy for us to actually swap this out with a solid state LiDAR if you want to, and put that in there. But like I say, at the moment, with the characteristics and the operations that we're looking for, and considerations of things like durability and price points, etc., the sensor stack that we have fits very well with the class of compact tractor that we're building at the moment.
Okay, fair enough. A question that came in from the audience: what interface is used for planning pathways for autonomous work? So they'd like to know, what are you doing for, I guess, routine sort of operations pathway work that would require normally would require an operator, and you're proposing would be done autonomously.
Yeah, and so the way we do that, we have two main classes of autonomous routines that we have on this tractor. We have the classic ADAS functionalities, where we really assume that an operator is going to be on the tractor or close to the tractor, and our ADAS functionality will take over one or more of the controls of the tractor. So I think you saw in our online video, we have an autonomy mode called gesture mode. And basically, gesture mode is a mode where you can get off the tractor, initiate the autonomy mode with your phone, and you will use the front cameras to actually use hand signals to drive the tractor around. Make the tractor go left, make the tractor go right, reverse, come forward, etc., etc. It's an example of an ADAS function. Another ADAS function that we have is something which we call row following, vine row following. So if you're entering a vine row and you don't want to steer anymore, you can basically press a button. If the tractor says, I can recognize this vine row, you can press a button and you will go down the vine row. So a lot of our ADAS functionalities is to make the life of the driver a lot easier, both in terms of, can I take this tractor autonomously down a row? rather than sitting on the tractor and having to get off every time I want to put something in, then getting back on the tractor, driving it a bit more. Can I actually just tell the tractor to follow me, and then I'll put something in the trunk, follow me, I'll put something in the trunk. So autonomy for us is not just the full sweeping, can I get this tractor to self-drive and basically go up and down the field, furrowing a field. So a lot of the base utility in terms of how you want to introduce automation into a farm is actually, allowing the driver to get on the tractor, but making his job easier and easier and easier to the point where he wants to get off the tractor. Moving a bit further along, we have another autonomy mode that we offer. We call it Copycat Mode. The Copycat Mode is where the driver can basically sit in the tractor. He can say, start recording my actions, and he will drive the tractor. Maybe he'll drive the tractor down a vine row and he'll switch the sprayer on and spray. He'll get to the end of the vine row, switch the sprayer off. Maybe he'll turn around, go down the next thing, spray on, spray on, spray off. And then he can hit record that. And what it does is we record that section of what the driver was doing. At any particular point in time, the driver can say, go and re-execute that routine. And what the tractor will do, it will navigate to the starting point of where that routine should execute, and basically go and do the same thing again. It's kind of like a progression from our ADAS functionality, where now what's actually happening is the tractor is taking full control of the tractor, but the driver is still there in case you want to do anything. So again, it's easing the burden of what the driver has to do. And then we go all the way through to what we call mission planning, which we have an application, which is our mission planner, which sits inside the cloud. And you can do your typical things. You can say, okay, based on the map, what I want to do is I want the tractor to go to this field, go to the beginning of this vine block, spray these 6 rows, go at 4 kilometers an hour, press the button, formulate the plan, send the plan down to the tractor with specific guardrails about, am I ready to do that? Do I have the right implement attached? Will actually go and automatically execute that plan. And so our autonomy stack goes from everything from the very simple, I'm going to take control of the steering because I want to be able to gesture, all the way through to, I'm watching what you're doing and I'm going to replay what you're doing, through to the full AI planning capabilities of, you want me to go and spray these 6 rows? What I'm going to do is, based on the knowledge of my map, I'm going to plot the best path through those 6 rows. And based on the implements that you want me to do, you can tell me when to switch on, switch off, switch on, switch off, switch on, switch off, as an example. So that's basically how we handle the path planning functionality. It's an application which sits on top of our base autonomy functions.
Okay, so to just sort of clarify on that last point, Chris, then there is essentially a functionality that if you had a farm or a certain set of fields or something, you could eventually get to the point where you are mapping them with the tractor, correct? And then
absolutely.
Yeah, and then it would go on to then implement certain actions that you desired within that.
And you may, that was a good catch there. I mean, basically, so there's an area that I haven't talked about, which is our SLAM capabilities, our simultaneous localization and mapping. I touched on the localization, but this tractor is also equipped with the sensors to basically gather the information so that we can make suggestions around what's on the farm, and those suggestions can be validated again in the cloud by a farmer. So a few things we do. Without giving too much away, if an operator's driving this tractor and he's driving past, say, the beginning of a section of vine rows, with these crop cameras we have on the sign, we will basically geofix the position of each of those vine rows.
Right.
So very, very quickly now, just by driving along the trails in a farm, we will actually record where the positions of each of those vine rows are. I'm giving a vine row example because we do a lot of our testing in vineyards at the moment. That will get passed up to our cartography tool, and all of those positions of the vine rows will be shown to the farmer. And the farmer can maybe adjust those a little bit. He says, no, that's not really a vine row. Yet those are vine rows. I'm going to actually put those into the map. And once those have been validated, they get loaded back down into our autonomy stack. And that is now a validated set of vine row positions. And based on that information now, you can do those operations whereby you say, okay, go and spray row number 1, 2, 3, 4, 5, and the tractor will use the geo information that it has to actually navigate to 1, 2, 3, 4, 5, and then plan the best routes. So it's just an example of how we do the auto discovery. Second thing we do, let's say you've taken the tractor to the geolocation of a vine row, and basically our autonomy stack says, I know I'm at the beginning of a vine row. Do you want me to auto navigate down? Now the tractor can auto navigate down. Something else we do when we're auto navigating down is we can see where every vine is. So now we can geolocate every vine in the farm. And that gives us a further level of sophistication on our SLAM capabilities. Because now when it comes down to vineyards, we've basically auto mapped everything. We know where the vine rows are, we know where the vines are. When we get to our more advanced data processing capabilities where we're capturing the images of the vines when we go past and basically providing kind of like slidable views about how vines are progressing through the years every time I've driven up and down, you can start to see the power of what we're doing in the roof with the data sets that we're collecting, the analytics in the cloud, and how that plays back to how we can actually automate the operations on the farm. It gives us a very powerful, kind of like very big control loop in terms of how we want to automate the mission plan.
Okay, great. Well, that sounds like a good solution and a good point for most types of typical duty cycles, at least anyway. A good starting point. We'll get to a little bit of the actual sort of mechanical aspects here with a couple of questions, and I'll combine these, I guess, into one sort of overall question about power, torque, those sorts of things. We have several questions coming in about that. One, how rapid is the torque and the amperage decay with maximum continuous torque output? So this person from the audience would like to know, basically how long is the battery going to last with, under a continuous high strain? And then another asks, what is the range at full charge, just in general? And I know that's not exactly like highway range or anything like that, but maybe you can just give some insight onto operation time at certain load levels, that sort of thing.
Sure. Yeah. So obviously that's pretty dependent on the operation being used. With a tractor, most of the power and energy is actually going into the implement or into the work you're doing. The driving over the terrain is actually a pretty small fraction of the total energy usage. So if you're doing a very high energy, high power kind of operation, right, your operation times are maybe on the order of 6 hours or somewhere in that range. For kind of a more normal operation, we've been seeing like 8 to 10 hours of operation from a single charge. And I think we're in the tractor is a compact utility tractor. So it's basically a 40 horsepower continuous tractor. But the nice thing about being an electric system is that means we actually do have a peak power capability that you wouldn't see in a conventional diesel tractor. So we're a 40 horsepower continuous, but our peak can be up to 70 horsepower. So if you've got a short duration, I need peak horsepower for 30 seconds or 60 seconds to pull out a stump or something like that. We have the capability to do that because of the kind of inherent advantages of an electric motor. Okay, great. Is the charge port J1772? I imagine with their use of primarily automotive components, it is. But yeah, okay. You've already mentioned, I think, or at least I saw it somewhere, level 2 charging. Is level 3 charging also possible? We are basically at the kind of maximum charge level for level 2. So kind of the top end of level 2. The DC fast charge, the kind of infrastructure implications of that for a farm are pretty significant. So we focus more on kind of getting as much as we can out of a level 2 charger. And
Zachary, I think you mentioned somewhere in the material that I saw how long a charge takes at level 2, 220, 240 volt. Could you remind everybody about that?
Yeah, it's generally 4 to 5 hours
Okay.
to do a full battery charge.
So certainly overnight, no problem. Then you've got
Yeah, no
everything
problem.
going, and no problem there.
Yep.
Okay. Chris touched on this a little bit at the initial part of the walk around. What's the weight split front to rear of the standard unit in terms of, I guess, just weight over the front axle versus the rear axle, and is that pretty much like a setup like a conventional tractor today?
We're a little bit more front biased than a conventional tractor. We're in the like 55 rear, 45 front kind of range.
Okay.
A conventional tractor is usually a little bit more rearward biased. So what that means though is that we're actually in a better situation for running rear implements, because most tractors, to run a rear implement, they'll load up the front of the tractor with a bunch of weight plates and put additional wheel weights on the front wheels often. So we basically, for implement work, we are much better suited, and we can actually do the implement work at kind of a lower total mass or lower total weight of the system because of the weight split we have.
Okay. Question on the PTO. Does it have torque sensing capability? If torque is too high, will it alert the operator or limit the torque? Can the end user set different torque limits based on the application or the implement?
Yeah, so we do have torque sensing thanks to the electric motor. So we know basically exactly what we're putting out of the electric motor, and we have very precise control over that. So we can limit or ramp down the torque on the orders of tens of milliseconds. So that ability means that we can set those kind of limits and can expose that functionality to the user so that they have the ability to say, limit my power output to X because the operation I'm doing, I know it shouldn't take more than this amount of power.
Okay. This is another combination question. Several people are asking, Zach and Chris, this is very much a high-end unit with many high-tech features. Will Monarch offer just a basic, simple electric tractor requiring the operator to operate it without all the high-end features? And I guess primarily the folks are asking, do you intend to maybe just make an electric tractor without any, in kind of inclusion, let's say, of anything for autonomous operation?
That a variant like that is kind of in our long-term roadmap, but honestly more for developing nations. So that is in our roadmap, but in the short term, we're very focused on kind of the tractor you see here. And that's really driven by the economic analysis that we've done, where if you look at kind of the cost offset of diesel fuel and the cost offset of tractor driver labor, the combination of electric and autonomous is quite a compelling economic case, particularly in California, but honestly throughout the world, but particularly in California. And so that is that's kind of why we have both. Is the economics are actually better when we have both than if we have one or the other.
Okay. Had a question here, a couple of questions also about work in canopy situations. I guess since a lot of the sensing really is done with machine vision, I don't know, that GPS is absolutely required, but that's what folks are asking, at least anyway, Zachary, is, what's the operational outlook look like for canopy situations?
Yeah, so I think there's two things there, and Chris can maybe describe it in a little more detail, but at a high level, the vision and the localization systems on board do not require the GPS. We can do it based on what the obstacles that we're seeing. So the interesting thing is in canopy, I have a whole bunch of trees or bushes or whatever. I have a lot of things in my visual field of view that I can use to figure out, okay, how do I stay in the center of all these trees or the center of all these bushes? Chris, did you want to elaborate on that at all?
Yeah, I mean, absolutely. I mean, you need various levels of position depending on where you are in the farm and different operations. Are very if you want to get 2 centimeter accuracy, then yeah, you need very clear view of the sky. But if you're in a vine row and you can auto navigate using the vision sensors. If you're in an orchard and you want to stay in an orchard row, you can again use the vision sensors to say maintain left and right. You can use various, and we do this sometimes in our localization strategies. We have known beacons or known objects in the farm where we can do localizations with those beacons, fairly standard. So we're not solely restricted to the GPS with respect to our localization. Our localization, like a lot of the autonomy stacks, use a Kalman filter, which takes in various data points for evidence in terms of where we are. But there are certain autonomy functions where you need very high levels of position. If you want to fully automate very precise copycat function where we're doing the same thing in the same position at the same in the same sequence, then we have a high localization confidence. But if all we're telling the tractor is to go to the beginning of vine block number 45, and we can calculate that through heading and wheel odometry and looking at various known categorized points from our object detection along the way, and actually get there and then see which row we're in, then go down the row. It really depends on the operation that you're automating in a farm.
Okay. Combining a couple more that is still on the operational aspects. Could you currently deploy this tractor from barn to field to barn without putting a driver in the seat? Sort of a variation of the one of the earlier questions.
Yeah, I mean, we do that all the time in our testing sites. So we have a vineyard that we this is why it's so dirty. We just brought it in today. We don't have a barn. Basically, we have a set of containers, and this is where the tractor sleeps. So she goes back at night, and she auto navigates to the container. We drive her the last thing, mainly because we have to do a couple of preparation things before we put her to bed, and then we plug her in. And then in the morning we come back and we unplug her. We bring her out, and then we tell her where we want her to go, which particular waypoint or which particular vine block we want to do, and that's how we do our autonomy testing. So the whole purpose of what we're trying to do, here is have as little human intervention as possible if necessary. And so to do that, what we do with our SLAM is to build up those very sophisticated maps. The maps that are sitting inside the roof, they're essentially a segmentation of the environment. So the geofence that the tractor lives in, the locations of all the fields, and the locations in the vine row that we're testing, in the vine vineyard we're testing at the moment, the location of all of the vines and the vine stems, known objects along the way. So if there's any buildings that you need to avoid, where the roads are, the speed limits on the roads, whether these are shared roads or whether they're dirt tracks. Basically, the path planning algorithm in the top uses that level of decomposition on the map, and then, as I say, we supplement that with the proximity map. So if we're going down the road, and I don't know, someone's parked their car there, we have a choice. We can either try to auto navigate around the car, or we can stay there and send a user alert to say, hey, what should I do? Do you want me to try to go around, or do you want to wait? And so, yeah, the whole notion is basically to go from the barn to your theater of operations, do your task, and actually come back. And that's what we do with our mission planning software.
Okay. Maybe a little bit related to that one, Chris. How does the tractor make turns at the end of a row if it's autonomously piloted? Do you run the entire route with a human and learn the route, or is it able to sort of autonomously make the decision itself that, okay, I've reached the end of a row, time to start another one?
Yeah, I mean, again, if we tell a tractor, for example, to go and basically to go and scout a vine block with and the vine block, because we know the geopositions of the end of each of the vine rows. The tractor will basically plot its best path based on its known kinematics, the turning radiuses, etc., etc. So it will auto calculate its turning radius, and then if it can't make it because, for example, there's not enough headroom there, then maybe it will come out back up, do a 3-point turn, and then go back in. So the path planning software in the roof is capable of doing that, and that's essentially what we have to do, because we can't have the farmer drive around every turn. So we have the kinematics of this particular tractor in the software, and we plan and we adjust, and basically we learn to adjust the kinematics over time. In reality, what happens a lot of the time, because the operations on the farm, the way that you get scalability through your automation is for looking for repeated operations. So what you tend to see over time, when you actually if you look at a heat map of where this tractor's been and our test sites, you're doing the same thing. You're going the same route, because you're spraying a block. So over a period of time, you start to get the breadcrumbs of where you are. And so you can start to use those breadcrumbs then to actually say, oh, this is what I did the last 20 times when I went round, which you can incorporate that into your mathematical calculations for the path planning. So we use a combination of things. We basically use the very, very precise fixed geo information on the map. We use the historical evidence of what we've done in the past, and then we supplement that with fine tuning with the vision systems.
Here's a specific question about the external temperature ranges. Any practical limit on sort of the ambient temperatures to use the tractor?
No, I mean, we cover the full ambient range that you could expect to see pretty much anywhere in the world. So -40 to +50 C ambient is no problem for us.
Okay. Does the path planning software take into account the implement length, width, overhang, the footprint, in other words, of an implement that you've attached?
Yes and no. We have a known. So basically, we certify this tractor with a set of known implements. So we have a library of implements, and so for that, because we've got that library and we've trained and we've worked out the interfaces, we know the measurements, and more importantly, we know how to do various autonomy functions like auto alignment. So if we've got the models in there. If a farmer's got an implement that we don't know, we can use certain classifications like is it a hitched implement? Is it a wheeled implement? Is it a 2-wheel, 4-wheel? Is it a fixed drawbar or a flexible drawbar? All those will make a decision about which autonomy routines we can actually run using this unknown implements. And then we will allow the farmer to actually specify the length and the width. So I would say there's 2 answers to that. If you want to use the full suite of the autonomy functions on the tractor, then the tractor needs to have a certain amount of knowledge of the implements that are on there. If you have implements that we haven't certified with, there are certain autonomy functions that won't work very well unless you actually provide us with that information through the implement interface that we have. We have an interface on our mission planning software that allows us to actually draw the implements, and we'll put you can enter those dimensions in. But I would say it's like everything else. If you're driving a car and someone just puts a thing on the back of your car and you've never driven it before, probably
Right.
90% of the stuff you can do, 10% you're going to make a mistake.
Yeah. Okay, fair enough answer. And I think it's just safe to say the damn thing's fairly smart on its own, and then from there you need to help it out a little bit. Then if there's
yeah. And so as part of our roadmap, there's part of what we do in autonomy is try to increase over time the self-learning capabilities of the tractor, not just in understanding its environment and learning from the environment, but also collecting with all of the videos and the information we collect, looking for suggested object classes. And you're right, basically, we can do a certain amount of that in the future. because we've got the cameras at the back, we can actually watch if someone's driving the tractor manually with the implement on, we can actually watch the implement and see what it's doing. And so over time, as we go on, we will make those self-learning capabilities on the implement a little bit smarter.
Okay. There's some curiosity about the steering itself. Is it drive-by-wire? Was it developed by Monarch, or have you used an existing electromechanical steering mechanism developed by a supplier?
It's using an existing hydraulic steering system that is used on many existing other tractors. Yeah, okay. Most tractor steering is hydraulic.
Okay. Well, this is really a market-based question, but I'm sure a lot of people are curious about this. Why did you decide to make a 40 horsepower continuous size tractor? In other words, a compact tractor. Over the years, tractors and implements have been getting larger and larger, mostly to reduce the labor operator costs by using larger tractors with less operators to accomplish more work. Do you expect farms to tend to switch to smaller tractors, but more tractors without operators in some type of a swarm kind of a situation? Or was the tractor size determined by a technical limitation?
The tractor size was actually determined more by the market research. So the 40 horsepower and around that class of tractor is actually the highest volume sales per year. The kind of compact utility tractor, like even the big farms, sure, you'll have your 500 horsepower tractor, but then you'll also usually have a compact utility tractor for other operations on the farm, kind of across the board. And then it's also the compact utility tractor class. A lot of people that have, whatever, larger, some amount of land or a small ranch or a small acreage, right? That compact utility tractor class is very prevalent as well. So it's actually that it was more market driven than anything else. And the swarm concept is definitely something that we talk about. I think that's more in the somewhat distant future. In the short term, though, your big commodity crops, your like wheat and corn and soy and those kind of things, yeah, all of that industry is going towards bigger and bigger tractors. But if you look at a lot of the stuff that's more on the vegetable side, grapes, nuts, orchards, a lot of those kind of food, those kind of crops, those markets usually have a lot of times have much smaller tractors because they need the smaller tractors to be able to get down the rows or down the orchard, down the vine row. So they still use a lot more smaller tractors. And actually that a lot of that is in California. A lot of the California farms are more that type of crop versus the Midwest farms where you're going to get a lot more corn and soy and whatnot.
Okay. Chris, I think you probably addressed this one, but maybe we'll ask just for a little bit more detail here. Another question asks, what kind of autonomous or automatic emergency braking system does this have when it comes to farm worker or pedestrian interactions? Maybe just hit that one more time.
Yeah, sure. During autonomous operations, what we do is we maintain a safety buffer around the tractor, which is why these things are flashing with a human detection. So when we're in autonomous mode, it's generally around about 2 meters. We have a 2 meter buffer. So if this tractor is moving backwards or forwards in autonomous mode, and anyone steps within that buffer, the tractor will stop. And so basically, we will within 2 meters, we will do a controlled emergency stop. If we detect a human a bit further out, we will come to a gradual stop. So again, we hook into the braking system of the drive-by-wire. So and it's a particular requirement of mine that we actually keep when we're in autonomous mode and we're flashing the autonomous modes, we keep the workers away. So I would say, yeah, we have everything from you get too close, we're going to stop the operation, through to if we see you a little bit further away, what we'll do is we may flash the lights, we may sound the horn, but eventually we're going to come to a stop. And it's not just with the forward and backward motion. As I mentioned, we have a similar thing with a PTO. Most of the industrial accidents on the farm are to do with a PTO. People getting their clothes or getting their hands too close, even though they've got protective sheaths on. A lot of the industrial accidents are on the PTO. So the same thing, if anyone gets too close to the PTO, we break the PTO and shut it off. And so that's basically it's part of our human to machine interaction. Get too close in automation, we're going to first of all we're going to protect the human, even if it disrupts our farming operation.
Right. Someone asked about animals. What about cows and dogs and that kind of thing?
It's a policy decision. So again, all of our guardrails, when it comes down to the classes of what we can detect, it really depends on the farm. Me being an animal lover, I will stop for any animal I can see. But if you're running a spray operation and you want to get it done that night, and there's a few coyotes in the way, maybe you'll nudge them out of the way. I don't know, but it's a policy decision. But all of that is configurable in the autonomy systems. The only thing that's not configurable is the human side.
Okay. Someone's curious about top speed in an autonomous mode.
Yeah, so the tractor top speed, just the baseline mechanical part can go about 20 miles per hour.
Okay. And is there a plan to use this in sort of potentially for non-farm applications? Someone specifically mentioned airports and that kind of, that kind of duty. Is there potential for that there? I guess you wouldn't tell somebody no, right?
Yeah, there's definitely potential there. And there's a number of active conversations that we're having with kind of different adjacent applications in many places, maybe not in the US as much, but in many places, the tractor is kind of the default workhorse to get jobs done, right? So you'll have tractors on road repair crews, you'll have tractors kind of all over the place because they are that mobile power source. So yeah, there's more than just the farm field that we see as opportunities. Okay, a couple of sort of regulatory and compliance type questions. Does it comply with ISO 18497? I'm afraid I don't know what that one is, so you'll have to help us out there. Anyone know that one? ISO 18497? I might need to look that one up specifically, but there's basically the big ones that we are that we are complying for is kind of the rollover protection system and falling object protection system. Those are some of the primary requirements, and then kind of all of the high voltage safety from automotive, and then some additional a lot of the safeties that Chris was talking about more on the automation and human interaction side. Okay. How about European standards? Does it meet European standards, and can you sell the tractor in Europe? Or is we are working towards that. The European kind of certification process is more burdensome than the US one. So we're working towards that, but we're not quite there yet. Pretty soon. Okay. We might as well get into this one quickly here. I know we're sort of running through the more pertinent questions here, but this one I think is one that probably on a lot of people's minds who are familiar with sort of the off-road industry, at least commercial vehicle industry off-road. I've read some articles about John Deere customers who are frustrated because their machines are becoming too complex. I've also seen some of these stories, where they're locked out by the software. If something goes wrong, the dealer insists on getting involved before the tractor can get running again. And an earlier question, Zachary also asked, are you worried about the complexity factor here for people who, farmers who have largely been dealing with, fairly straightforward mechanical systems all their lives? Sure. Yeah, so we definitely support the right to repair and have actually designed the system to help with that instead of actively hinder that. So we have a kind of a built-in user manual that is, because it's connected to the tractor and because the tractor knows the state of all of the sensors and all of the actuators on the tractor, we can actually give the user more insight into like, hey, this is where the issue is, right? This is the thing that we need you to help us look at. And so we're actually kind of on the opposite end of the spectrum there. And I think there's kind of a balance, like there is obviously more technology than a conventional tractor. But actually from a maintenance standpoint, going electric right? The kind of a lot of the maintenance and the oil filters and all of the engine maintenance, and now a lot of the diesel exhaust filters, which are causing quite some challenges for a number of current generation tractors. All of that is kind of eliminated from the system, so it's a balance. But I think our philosophy is much more that we not only want to help farmers be able to repair the tractor, we actually want to help them be able to develop kind of next generation implements that make use of the functionality that we have on board the tractor. We really want to see it become a platform for future innovation instead of a lockdown system that doesn't allow you to even fix what's already there. We want to kind of go to the 180 of that.
No, it sounds like a wise positioning there, I think, and I agree with you. I do think that as we, as we've seen in other industries, as electrification takes more hold, the complication, the productivity of the vehicle itself, all tend to increase because there just simply aren't as many things to break, and you don't have as many fluids, all those sorts of things. You mentioned exhaust particulate filters, everything. It's all becomes largely a lot more simpler. So, that's always a good thing from a systems outlook, at least anyway. Benjamin Binns, I wanted to call out real quick. He gave us the answer to ISO 18497 from 2018, agricultural machinery and tractors, safety of highly automated agricultural machines, principles for design. So thanks for that one, Benjamin. We all got a little bit of an education there that don't carry all those numbers around in our head. So as you said, Zachary, mostly dealing with safety and of automated agricultural machines. So thanks again for that. Someone here wants to know what was the makeup of the team that developed this tractor, and how long has the tractor been in development?
Yeah, I mean, it was a pretty relatively large team. Well, okay. Small compared to tractor companies, moderately large compared to two-person startup. So yeah, kind of call it a mid-sized team that developed it. Really, the tractor that you see there has been in the field for the last year, and it took us I think it was like 9 months before that to really develop it from clean sheet to getting it in the field for the first time, and then it's been running in the field for the last year. And yeah, that team was kind of a combination of the Monarch team who's on the call today, and then Monarch was actually a spin-off of another company called Motivo Engineering, which is more of an engineering services company. So those two teams working together, the Motivo team and the Monarch team, are worked together to develop this, and so that's why we were able to do it so quickly.
Okay, how many people can you count it up exactly?
It varied fairly significantly across the duration. I would call it somewhere between 20 and 30 people on average, but there were definitely spikes above that and some other times when it was a little bit less than that.
And how long overall? Do you care to answer that in terms of,
It was about 9 months for the tractor you see there. There was about a 9-month design build cycle, and then it's been under test and kind of software firmware development for the last year.
Okay. Directionally, in terms of service expenses, someone wants to know where do you see that going? Obviously, you've already said down a little bit, and I think you said $4,500 a year in overall operating expenses reduction. Was that the number that I saw?
Yes, somewhere in that range. Some of that depends on like how much you drive it and what the diesel fuel offset is, and then also what the maintenance is. We expect it to be similar to the automotive industry, where there's been a number of studies now that have shown that electric vehicles usually have like between 1/3 and 1/4, or so like only 25 to 30% of the maintenance cost of a conventional internal combustion vehicle. So we expect to see a similar reduction in maintenance cost.
Okay, good. What chemistry batteries are you using, and what is the expected life of the battery pack itself? Little bit more detail there.
Yeah, so I mean, we're using a lithium-ion chemistry and NMC variant, and the lifetime we expect it to last about the lifetime of the tractor, which is kind of a 10-year base. That's what the warranty's at. The tractor itself will last beyond that, and the battery pack, structure, just the active chemistry might is where we're looking at kind of that 10-year range.
Okay. I know in my neck of the woods, there's a lot of guys running around tractors a lot older than 10 years.
Yeah, I know. The tractor itself is much longer than that. The battery, there'll be.
I'm just playing
10-year
devil's
horizon.
advocate there because, that always comes into it. Someone here just makes a comment. They're looking forward to hydraulic being replaced by electric auxiliary power for the implements, and they're pleased to see about that. And we have a question here about soft and unstable soil conditions. Does the tractor know when it is approaching soft soil conditions in a field and avoid traveling into a sinkhole situation? What can you say about that?
I think there's two parts to that. So one is that if we start to enter a sinkhole or something like that, or start to enter a mud puddle, the inertial measurement unit on board and the various wheel speed and wheel slip sensors that we have, we can detect that and basically stop continuing to drive into it. Mm-hmm. And then I think the other aspect of that is that, to Chris's discussion earlier about kind of the map that we're generating, right? Most farms, you don't have a random sinkhole. You have this corner of the field always gets wet and muddy. And so we learn that over time. And so we know, we know what the weather is. We know that it rained yesterday. We know that what the soil conditions are, generally because of looking at the torques and speeds and slips on the tractor. So we know what's happening, and we know that this part of the map is where the sinkhole is going to be. So we can, in that sense, we can avoid many scenarios. But if you're, just driving on a stretch that you haven't seen before, then it's more of a don't keep getting deeper into the mud puddle.
Right. Okay. I think Chris talked about this a little before, but maybe we can just hit this again. Can the tractor handle road and traffic laws without a driver? Basically, public road operation. What is your sort of outlook on that?
No, this is not for public roads in terms of the autonomy stack. We call the autonomy stack a farm-focused AI stack, and so the maps and the hazards and all of our autonomous routines are geared towards agriculture, not for urban driving. In fact, I don't even think Zachary, correct me if I'm wrong, just from a physical hardware platform, I doubt if this tractor is allowed on the road in its current state.
Yeah, we need to put the slow-moving vehicle triangle on the back of it to do that, which we can do. So, right. But yeah, and honestly, it's an interesting thing for us, especially compared to kind of autonomous vehicles. In some sense, it's less of a technical limitation. Like, we haven't actively pursued that, but if we wanted to, we could. It's really the liability aspect, right? As long as the tractor stays on the farm property, it's a different liability situation versus as soon as you go out on public roads, that kind of changes the equation.
Yeah.
So the nice thing about farms is that we can avoid that whole kind of tangle that autonomous vehicles find themselves in by staying on the farm property.
So just going back to the regulatory question. So there's, for example, in California, there's a different regulatory body that we look at when it comes to our autonomy routines than if we were on a public road. So the agency, which is largely more concerned with automation in farm environments in California, is CalOSHA, the Occupational Health and Safety, because they're really concerned about how these autonomous systems interact with humans. So it's, if we wanted to actually look at the regulations for automating on a road, we'll be in a different class of regulatory discussions.
Okay. Last few here, maybe. I think everyone's probably getting a little wrung out. Any plans to mount a solar panel on the roof to charge the tractor at the farms? Is that at all feasible?
We've looked at the numbers, and generally it doesn't work out. What is highly feasible, though, is many farms are installing solar panels. It's actually it's in its infancy, but there are a number of farms that are actually doing combined solar and crops, where you basically in the fields, you have solar panels and crops next to each other. And so the solar array at the farm and using that to recharge the tractor and potentially go to a net zero carbon system if you wanted to, that's definitely a possibility. But the power levels of the tractor necessitate a much larger solar array than you could. We're like
Right.
2 orders of magnitude off in terms of the number of solar panels you would need. So that's it's more like put the solar panels on the farm. We'll charge from those.
Okay. What is your position on brokering data collected with or without the knowledge of the tractor owner? Is your information your own information?
Yeah, all of the data that this tractor collects belongs to the farmer, and so again, it comes down to a couple of decisions. One of them is the data regulations, depending on the environment we're in. So whether we're in Europe or North America or in California or the state regulations. But our philosophy is the data belongs to the farmer, and the farmer can decide whether they want to share with Monarch, and the farmer can decide whether they want Monarch to share their data to third-party providers.
Okay, very righteous position. I'm glad you have.
Absolutely.
Okay, someone, and I guess, we've talked around this a little bit, but this is a good question, and one that I wonder about with autonomous passenger vehicles, out on the road and in parking lots. Does the perception system distinguish between a person or a tumbleweed? If it can, does it know it's safe to proceed in the case of the weed, or does it always stop?
Again, it really depends on the policies of the guardrail. So for us, we're highly trained on humans, and so we test our perception systems to have a 90% confidence within 10 meters, depending on the lighting conditions. And so, going back to the safety envelope that I talked about, our philosophy always is, if we're in autonomous mode and you're close, we will stop the operation. That's our default, and we don't really let anyone override that default. The separation of different objects that we see, for example, whether it's an animal, whether it's a tumbleweed, whether it's a car coming from the left, car coming from the right, it's the policies that we have dictated by our guardrails. And so one of the guardrails, a secondary guardrail we have, which is to do with vehicle protection, is we will do when we're coming up to a junction on the farm, we will always stop, and we will look left and we will look right, and we will look for moving traffic before it's safe to proceed. So, your perception is really dependent on two things: the class of objects that your cameras can recognize, and then the policies that you have around what you do with those objects. And then the default category is anything which your point cloud, whether it's an optical point cloud or whether it's a LiDAR point cloud, tells you is there and that you can't classify. So actually, a lot of the important things for us are clumps of points that we're seeing in front of the tractor that we can't classify. In that instance, we will always stop. And at that particular point in time, it's really up to human intervention to say, what do you want me to do? Like I say, for us, I've been in automation for more years than I can care to remember. Safety first. With something like this, operating in a farm environment where you're in a fairly dynamic environment where you're interacting with humans, safety is even more important.
Okay. Well, I think most of the remaining questions here are most variations of everything we've kind of hit you with so far. So I think unless there's anything you want to wrap up with, Chris or Zachary, I'll hand it off back to Delbert Boone, and we'll see how we want to close here.
I'll let you have the closing words if you want, Zachary.
No, I think I'd like to thank everyone for sharing part of their evening with us, and definitely I think there's the website, and if there's any additional information, that definitely feel free to reach out for if there's additional questions. If you want to reach out directly to Monarch, we'd be happy to answer them.
Yeah.
Oh, good evening, everyone. My name is Delbert Boone. I am the Vice Chair for the Meeting and Tours Committee for SAE SoCal section. I'd like to personally thank the Monarch team, as well as our SAE colleague from International Headquarters, Bill Visnick, for hanging out with us at such a late hour. He's located on the East Coast. So thank you guys for such a great webinar and great content. Also to the participants, thank you for participating. I'd like to update you on some of the upcoming events we have for our SAE SoCal section. In January, we have a two-part event, which is the Road to 2035 EVs in California. The first event will be the 19th. The follow-up event will be the 27th. Also, on February 3rd, regarding SAE SoCal, if you'd like more information, we have listed our links for social media as well as online. Our website is www.saesocal.org if you'd like to find additional information on upcoming activities. If you're also interested in joining our section, you will find a membership tab within that web link. And then last but not least, if you want to get involved personally with myself on the Meeting and Tours Committee, or if you're just seeking additional information for the membership, our emails are listed. Myself, Delbert Boone, which is meetings.tours@saesocal.org, and Dean Case, which is our membership vice chair at saesocal.org as well. Also wanted to thank Joey Penniman, who's the section chair for SA MidCal. For those participants that would like additional information, Joe has listed his email as a contact, so feel free to reach out to him directly. And then last but not least, the Monarch AV Tractor team. They've listed their website, also the information, and then a phone 800 number dial-in. Motivo Engineering as well has listed their website. For anyone seeking additional information on careers, feel free to reach out to those organizations directly. So once again, I'd like to thank everyone, and hopefully we look forward to seeing you at future events. Good evening.